Hi there. Today we're going to be talking about wave-particle duality, and this time we'll be thinking about the context of particles acting more wave-like. Now, this wave-particle duality is obviously a real turning point in science as a whole. So what became fixed classical mechanics, we're now approaching the ideas of quantum mechanics and where the cutting edge of science exists. So this all started off with the photoelectric effect and recognition that photons confusingly seem to appear in clearly defined packets having a particle-like flavor. During this session we're going to be talking about how particles can be seen to have a wave-like flavor. Now this was hypothesized quite early on, and the theory was developed by a man called de Broglie. And de Broglie stated or thought that there must be a relationship between the energy of a photon and its overall momentum. So he theorized that the wavelength is going to be equal to Planck's constant divided by the overall momentum, which is P, or it could be Planck's constant is divided by mass times velocity, which is obviously the product which forms momentum. So this is his general theory. Okay. So he felt that everything should be able to be described as a wavelength if it has energy and hence has momentum. So here's an example of a question which asks you to consider de Broglie's wavelength. Find the de Broglie wavelength of a proton that has been accelerated from rest by a potential difference of 500 volts. So I'm going to pause for a moment, think about the information you know there, try and answer the question. Okay, so hopefully you've come up with an answer. Let me just see how you should solve this problem. We recognise that kinetic energy of a proton is going to be half mv squared, or this can be shown as the momentum squared divided by 2m. We know the work done is accelerating the proton through a potential difference. V is equal to the charge times the voltage. Okay, so that's going to be the amount of work done. Now this means that these two things are going to be equal to each other. So the final kinetic energy is going to be equal to the amount of work done through the field. So therefore I can rearrange this to show that the momentum should be equal to the square root of 2 times the mass times the charge times the voltage. Hence, if I place that new value or new formula I've got for momentum into de Broglie's original formula, I can work out by just putting the numbers in as required that the wavelength of this proton should be 1.3 times 10 to the minus 12 meters. So that would be the de Broglie wavelength of a proton in this situation. So this was, as I said, a theory which couldn't be confirmed or disproved, but it seemed natural that there be a certain symmetry within wave-particle duality. Now the first observations we saw which indicated that it could be this case was that of electron diffraction. Now in this case, if I have an electron gun and it's fired through a thin graphite screen, what was produced if we had an evacuated cylinder was what's known as diffraction rings. Okay, so diffraction was occurred due to the interaction of electrons. Just to go into a kind of a little bit more detail here, what was actually observed in this situation is something a little bit like this. What we can see is there be a central area where we'd expect the most electrons to exist, and then we have rings appearing, and these rings appearing, I guess, very much fit the idea of circular diffraction, which we've observed in light. Now, that gave a good insight, but it didn't give us a numerical confirmation of the situation. That came about from some experiments by two men known as Davisson and Germer. And what they did is that they were firing a beam of electrons at a nickel target, and they were then moving a detector and identifying where the electron beams which have been diffracted. Okay, so diffraction was taking place. Just to emphasize this, what is actually happening here is that the patterns appear to be similar to a diffraction grating. Now, diffraction grating isn't something we speak about on the standard level course, but just to say what happens here is the beams hit the metal, and what happens is that the structure of atoms and or gaps between atoms, atoms and gaps between atoms, means that the particles coming off here look a lot like light coming through a grating of lots of very, very small slits, and there's a related interference in this situation. So what happens is the nuclei act as obstacles of size B. Now, with a diffraction grating, it's known that the first minimum of diffraction is given by the sine of the angle to that minimum is equal to the wavelength divided by the size of the abstraction. This feature allowed them to confirm the prediction of de Broglie's wavelength, because using the wavelength values which were predicted, they were able to show that the electrons diffracted fitting this pattern. So this is quite a big finding. So suddenly we've got some confirmation of what was previously theorized, some observations which show what we're thinking about. Now, this will lead to some quite exciting steps as we go forward. What happens is suddenly de Broglie's wavelength can be put into context of different situations. So in the future lessons we're going to be talking about models of atoms and electrons in atoms, and actually how we can improve our model of a multi-layer atom by considering the wavelengths of atoms found around wavelengths of electrons found around an atom. So that's where we're going to be going to, and this was the first insight into this. Just going to spend one moment to look at one final question. This is probably more of a higher level style question because it thinks about the diffraction grating, but this is something for you to think about. In a neutron diffraction experiment, a beam of neutrons of energy 85 megaelectron volts are incident on a foil made out of lead and diffracted. The first diffraction minimum is observed at an angle of 16 degrees relative to the central position where most of the neutrons are observed. From this information, determine the size of the lead nucleus. So we're going to go about thinking about the size of the lead nucleus is going to be the size of the obstacle. So, similar to the example before, take a moment, try and answer this question, and then I'll explain how the solution takes about. If we know the mass of the neutron is 1.6 times 10 to the minus 27 kilograms, and the kinetic energy is 85 megaelectron volts. We know that the momentum can be the square root of 2 times the mass times the charge times the voltage, and this comes out of a momentum in the end of 21.3 times 10 to the 20 kilograms per meters per second. The QV here, I note, is that we already have the value in megaelectron volts. It was just required a conversion rather than using the charge of the particle. Here I got my wavelength is the Planck's constant divided by momentum, which is 0.31 times 10 to the minus 14 meters. So that's my wavelength. Now if I use the diffraction formula, I recognize that B is going to be equal to sine 0.31 times 10 to the minus 14, which is the wavelength, divided by sine of 16 degrees, which is obviously the angle to the first diffraction minimum, so therefore gives me a value for B of 1.12 times 10 to the minus 14 meters, which is a suitable approximation. Hopefully you've now had an insight into considering particles in the form of waves.